And we're back and better than ever in 15-2, where we're still discussing homogeneous aqueous systems. In this podcast, we're going to take a look at hydrates, where a hydrate is a compound that has water trapped inside of the crystals themselves. What can happen is that when you have say a solution, something dissolved in water, you can allow that water to evaporate off. And what happens is, as the water evaporates off, you're left with salt crystals again. But in some cases, there is actually water trapped in those salt crystals, and that water is called the water of crystallization or the water of hydration. And so a hydrate is simply a compound that contains water of hydration. And I'll just put in parentheses, trapped in the crystal. Right? And in many cases, they're very, very predictable as to how much water gets trapped in there. Now, you can remove the water and determine how much water is in there. In fact, we will be doing that in lab. The pictures that you're looking at here are of copper sulfate pentahydrate. Right here, this is CuSO4. And the way we write the water that's trapped in there, we put a dot behind it, and then the amount of water that's trapped. So in this case, there are 5 molecules of water trapped for every unit of CuSO4. Or if you did it on a per mole basis, there are 5 moles of water for every mole of CuSO4 in the sample. And so as you heat this thing up, you'll notice that it, in this case, is a nice blue color. Not all hydrates are blue, but the copper sulfate is. When you heat this thing up, as you drive off the water, notice in this case, the compound is becoming a white color as the water is driven off. In this case, you'd be left with just CuSO4 without the water attached to it. That would be called the anhydrous version of the copper sulfate. Now, like we said, the hydrates are trapped in regular, predictable amounts. And looking at this table 15.2, you'll see that when magnesium sulfate traps water, it traps 7 moles of water for every mole of magnesium sulfate. The barium hydroxide traps 8 moles. The calcium chloride, in some cases, traps 2, and so on and so forth. The way we name these hydrates is by simply naming the compound and naming the hydrate based on the amount of waters, and we use the Greek prefixes to do that. So in this case, because there's 7 waters trapped in the magnesium sulfate, we call it magnesium sulfate heptahydrate, hepta meaning 7. If you have barium hydroxide that traps 8 water molecules, you have barium hydroxide octahydrate for the 8 waters. The calcium chloride dihydrate, copper sulfate pentahydrate, sodium sulfate decahydrate, and so on and so forth. All right, so you simply name them using the Greek prefixes. Now, these hydrates have various properties. Some of the hydrates will actually release their water into the atmosphere. If that happens, we say that the hydrate is efflorescing. An efflorescent hydrate releases water into the atmosphere. It will do that when the vapor pressure of the hydrate is greater than that of the atmosphere. For example, sodium carbonate decahydrate, so we'll put a 10 out front there. Let me redraw the dot. Sodium carbonate decahydrate will lose its water, so we'll say that that's a solid, and what you're forming is sodium carbonate anhydrous, and the 10 waters go into the gaseous phase, something like that. So that's called efflorescence. On the other hand, some of them will actually absorb moisture from the atmosphere, and that's called a hygroscopic hydrate. This absorbs H2O from the atmosphere. For example, calcium chloride will take on water to form calcium chloride dihydrate. And in fact, this calcium chloride is very useful. It's used as what's called a desiccant. A desiccant absorbs moisture, and so what you do is you have this big vase, and we will be using this when we do our hydrate lab. Okay, we'll put it on some type of pedestal here, something like that. There's a very thick rim on this thing, and then you put a lid over the top of it, something like that. And then there's a tray, and inside or underneath that tray is the desiccant, in this case calcium chloride. And so what can happen is, because this lid is sealed, any H2O moisture that's in this chamber gets absorbed down into the desiccant, and so it keeps anything that's in there very, very dry. And that's important because when we want to figure out how much water is in a compound, we're going to have to dry it inside of this desiccator. And as you dry it, water can actually be reabsorbed by the hydrate. Well, you don't want that to happen, so you put it inside of a desiccator. And this desiccant, the calcium chloride, does all the absorbing of the moisture. Anything that you put in there will, in fact, remain dry. All right. They also put desiccants in the pockets of coats and other clothing items when they're shipping them, because they don't want the moisture to build up in these pockets and eventually rot out the clothing. So you'll have these little things that these little packets that say "do not eat," and when you buy your coat, you take them out and throw them away, and then you're all set, and you have a nice fresh coat. Now, some substances will do this to such a large extent that they will dissolve themselves in their own water of hydration. And that's called deliquescence. Deliquescent compounds absorb so much water that they dissolve themselves. Sodium hydroxide is deliquescent. If you have solid sodium hydroxide, it will absorb moisture from the atmosphere, and eventually what happens is you'll be left with sodium hydroxide AQ, dissolved. All right. Lithium chloride does the same thing. All right, so you have hydrates that absorb moisture. They usually absorb it in a regular amount. In that case, you can include it and must include it in the formula of the compound. You name it using the Greek prefixes based on the amount of water that gets absorbed. Those hydrates that emit water, release water to the atmosphere, are called efflorescent hydrates. Those that absorb moisture are called hygroscopic. And those that absorb so much water that they dissolve themselves are called deliquescent compounds. In the next podcast, we're going to show you how you can calculate the amount of water that's in these hydrates that we're talking about. We'll see you next time.